Have you ever wondered what a black hole really is? Today, we're diving into one of the universe's most fascinating and mysterious phenomena, the black hole. These cosmic objects have captured the imagination of scientists and the public alike for decades. In this video, we'll explore what black holes are, how they form, and why they're so important to our understanding of the universe. Let's begin our journey by unraveling the basics of black holes and setting the stage for a deeper exploration into their secrets. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape from it. This happens because a massive amount of matter is packed into a very small area, creating an incredibly dense object. The boundary around a black hole is called the event horizon. Once something crosses this boundary, it cannot return. Black holes challenge our understanding of physics and push the limits of what we know about space and time. The force of gravity near a black hole is so intense that it warps the very fabric of space and time. This warping effect is predicted by Einstein's theory of general relativity. Near a black hole, time slows down compared to areas farther away. The closer you get to the event horizon, the stronger these effects become. This makes black holes not only fascinating objects, but also natural laboratories for testing the laws of physics under extreme conditions. Black holes are born from the death of massive stars. When a star much larger than our sun runs out of fuel, it can no longer support itself against gravity. The core collapses under its own weight, and if the remaining mass is great enough, a black hole forms. This process is known as a supernova, where the outer layers of the star explode outward while the core collapses inward, creating a black hole at the center. Not all black holes are the same. There are three main types: stellar black holes, supermassive black holes, and intermediate black holes. Stellar black holes form from collapsing stars. Supermassive black holes, found at the centers of galaxies, contain millions or even billions of times the mass of our Sunday intermediate black holes, are thought to exist but are harder to detect. Each type plays a unique role in the cosmos. Stellar black holes are the most common type. They typically have a mass between about 3 and 10 times that of our Sunday. These black holes are formed when massive stars collapse at the end of their life cycles. Although they are relatively small in size, their gravitational pull is incredibly strong, making them difficult to detect unless they interact with nearby matter. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way. These giants can have masses millions or even billions of times greater than the Sunday. Their origins are still a mystery, but they play a crucial role in the formation and evolution of galaxies. Scientists believe that every large galaxy has a supermassive black hole at its core. Intermediate black holes are thought to bridge the gap between stellar and supermassive black holes. They may have masses ranging from hundreds to thousands of times that of the Sunday. Detecting these black holes is challenging because they are rare and don't have as much surrounding material to interact with. However, their existence could help explain how supermassive black holes form. Some scientists theorize the existence of primordial black holes, which may have formed in the early universe shortly after the Big Bang. These black holes could be much smaller than stellar black holes, possibly with masses as low as a mountain or even less. While none have been confirmed yet, primordial black holes could help explain certain cosmic mysteries, such as dark matter. The event horizon is the boundary around a black hole beyond which nothing can escape. It marks the point where the escape velocity exceeds the speed of light. Once something crosses the event horizon, it is lost to the outside universe forever. This invisible surface is what gives black holes their name, as not even light can escape from within. At the very center of a black hole lies the singularity, a point where matter is thought to be infinitely dense and gravity is infinitely strong. The laws of physics as we know them break down at the singularity. Scientists are still trying to understand what happens in this mysterious region, as it challenges our current theories of space, time, and matter. One of the most dramatic effects near a black hole is called spaghettification. As an object approaches the event horizon, the difference in gravity between its near and far sides becomes extreme. This tidal force stretches the object into a long, thin shape, like spaghetti. This process would be fatal for any object or person falling into a black hole. Black holes themselves are invisible, but scientists can detect them by observing their effects on nearby matter. For example, when a black hole pulls in gas and dust from a companion star, the material heats up and emits X-rays before crossing the event horizon. These X-rays can be detected by telescopes, providing evidence of a black hole's presence. Another way to detect black holes is through gravitational waves. When two black holes merge, they send ripples through space-time known as gravitational waves. These waves were first detected in 2015 by the LIGO Observatory, confirming a major prediction of Einstein's theory. Gravitational waves provide a new way to study black holes and other cosmic events. In 2019, scientists captured the first ever image of a black hole using the Event Horizon Telescope. This historic achievement showed the shadow of a supermassive black hole in the galaxy M87. The image revealed a bright ring of light surrounding a dark center, confirming many predictions about black holes. This breakthrough marked a new era in black hole research. Time behaves differently near a black hole. According to Einstein's theory, the stronger the gravity, the slower time passes. Near the event horizon, time can slow down dramatically compared to regions farther away. This phenomenon, known as time dilation, has been confirmed by both theory and observation, making black holes fascinating objects for studying the nature of time. Black holes have long been a popular topic in science fiction, often depicted as portals to other worlds or times. While the reality is more complex, the extreme conditions near black holes could, in theory, allow for phenomena like wormholes or shortcuts through spacetime. However, these ideas remain speculative and are not yet supported by evidence. In the 1970s, physicist Stephen Hawking proposed that black holes are not completely black. Instead, they can emit a faint glow called Hawking radiation caused by quantum effects near the event horizon. Over time, this radiation could cause black holes to lose mass and eventually evaporate. This idea connects black holes to the world of quantum physics. The black hole information paradox is a puzzle that arises from the combination of quantum mechanics and general relativity. If black holes evaporate through Hawking radiation, what happens to the information about the matter that fell in? According to quantum theory, information cannot be destroyed, but black holes seem to erase it. This paradox remains one of the biggest mysteries in physics. Our own galaxy, the Milky Way, is home to many black holes. The most famous is Sagittarius A*, a supermassive black hole at the center of the galaxy. Scientists study the motion of stars and gas clouds near Sagittarius A times to learn more about its properties. These observations help us understand how black holes influence their surroundings. Supermassive black holes are thought to play a key role in the formation and evolution of galaxies. Their immense gravity can influence the motion of stars and gas, shaping the structure of the galaxy. Some theories suggest that galaxies and their central black holes grow together, affecting each other's development over billions of years. When matter falls toward a black hole, it often forms a spinning disk called an accretion disk. Friction within the disk heats the material to extremely high temperatures, causing it to emit X-rays and other radiation. Accretion disks are among the brightest objects in the universe and provide important clues about the behavior of black holes. Some black holes produce powerful jets of particles that shoot out from their poles at nearly the speed of light. These jets are created by the intense magnetic fields and energy in the accretion disk. They can extend for thousands of light years and are visible across the universe, providing another way to study black holes from afar. In some cases, black holes exist in binary systems with a companion star. The black hole's gravity pulls matter from the star, forming an accretion disk and emitting X-rays. These systems are called X-ray binaries and are important for studying the properties of black holes and their interactions with other stars. Some of the most powerful explosions in the universe, called gamma-ray bursts, are thought to be caused by the formation of black holes. When a massive star collapses or two neutron stars merge, a black hole can form and release an intense burst of gamma rays. These bursts are detected by satellites and provide clues about the most extreme events in the cosmos. Quasars are extremely bright and distant objects powered by supermassive black holes at the centers of young galaxies. As matter falls into the black hole, it releases enormous amounts of energy, making quasars visible across billions of light years. Studying quasars helps astronomers learn about the early universe and the growth of black holes. Some theories suggest that black holes, especially primordial ones, could make up a portion of the mysterious dark matter in the universe. Dark matter does not emit light or energy, but its gravitational effects are seen in galaxies and clusters. If black holes are part of dark matter, they could help explain many cosmic mysteries. Wormholes are hypothetical tunnels through space-time that could connect distant parts of the universe. Some theories suggest that black holes could be entrances to wormholes, although there is no evidence for this yet. Wormholes remain a popular idea in science fiction and theoretical physics, sparking curiosity about the true nature of black holes. Some speculative theories propose that black holes could be gateways to parallel universes. While this idea is not supported by current evidence, it highlights the mysterious and mind-bending possibilities that black holes present. Exploring these concepts helps scientists push the boundaries of our understanding of the universe. Black holes may play a role in the ultimate fate of the universe. Over trillions of years, black holes could slowly evaporate through Hawking radiation, leaving behind a cold, dark universe. Studying black holes gives us insight into the long-term evolution of the cosmos and the possible end of everything we know. Black holes have become iconic in movies, books, and television. From science fiction classics to modern blockbusters, they are often depicted as mysterious and dangerous cosmic objects. While these portrayals are sometimes exaggerated, they help spark public interest in real scientific discoveries and the wonders of the universe. Some black holes have become famous in the scientific community. For example, Cygnus X1 was the first strong black hole candidate discovered in our galaxy. The supermassive black hole in M87 became world famous after its image was captured in 2019. These objects continue to be studied for the clues they provide about the universe. Astronomers use a variety of tools to study black holes, including telescopes that detect X-rays, radio waves, and gravitational waves. By observing the effects of black holes on nearby stars and gas, scientists can learn about their mass, spin, and other properties. Each new discovery brings us closer to understanding these mysterious objects. Studying black holes is challenging because they are invisible and often far away. Detecting their presence relies on indirect evidence, such as the motion of nearby stars or the emission of X-rays. Advances in technology, like the Event Horizon Telescope and gravitational wave observatories, are helping scientists overcome these challenges and make new discoveries. Black holes are at the intersection of two major theories, general relativity and quantum mechanics. Understanding what happens inside a black hole could lead to a theory of quantum gravity, uniting these two pillars of physics. This quest is one of the most exciting frontiers in modern science. Black holes push the laws of physics to their limits. They challenge our understanding of gravity, space, time, and quantum mechanics. By studying black holes, scientists hope to uncover new principles that govern the universe and solve some of the deepest mysteries in science. Some theories suggest it may be possible to extract energy from a rotating black hole. This process, known as the Penrose process, involves using the black hole's rotation to gain energy. While still theoretical, this idea shows how black holes could one day be harnessed as cosmic power sources. The cosmic censorship hypothesis suggests that singularities are always hidden within event horizons, so they cannot be seen from the outside. This idea helps preserve the predictability of the laws of physics. However, some solutions to Einstein's equations suggest that naked singularities, visible to the outside world, could exist. This remains an open question in theoretical physics. Black holes are also linked to the concept of entropy, a measure of disorder in a system. The area of a black hole's event horizon is related to its entropy, as shown by physicist Jacob Bekenstein. This connection between black holes and thermodynamics has led to new insights into the nature of information and the universe. The event horizon of a black hole is defined by the speed of light. To escape from inside the event horizon, an object would need to travel faster than light, which is impossible according to the laws of physics. This is why nothing, not even light, can escape a black hole once it crosses this boundary. The intense gravity of a black hole bends the path of light around it, a phenomenon known as gravitational lensing. This effect can create distorted or multiple images of objects behind the black hole. Gravitational lensing is a powerful tool for astronomers to study black holes and the distribution of matter in the universe. Black holes play a role in the cosmic recycling of matter. When stars and gas fall into a black hole, some of the material is ejected back into space in the form of jets and winds. This process can enrich the surrounding galaxy with heavy elements, influencing the formation of new stars and planets. Black holes continue to fascinate scientists and the public alike. Their mysterious nature challenges our understanding and inspires us to ask big questions about the universe. By studying black holes, we not only learn about these incredible objects, but also about the fundamental laws that govern everything around us. To sum up, black holes are regions of space with gravity so strong that nothing can escape. They come in different sizes, from stellar to supermassive, and play a vital role in the universe. From their mysterious event horizons to their influence on galaxies, black holes remain one of the most intriguing subjects in science. Our journey to understand them is far from over. As technology advances, our ability to study black holes will only improve. New telescopes, observatories, and theoretical breakthroughs promise to reveal even more about these cosmic enigmas. The quest to understand black holes is a journey that pushes the boundaries of science and inspires us to keep exploring the universe.